if you now just wait long enough, you see the filaments are changing their phase. And slowly they end up being perfectly in phase and remain phase locked thereafter. So that's the same thing that's happening in the motor population. And this is a perfect example of what's called elasto-hydrodynamic synchronization. Again, there are two words, elasticity and hydrodynamics. What's happening is that they're generating this disturbance velocity field because of the oscillation, and that generates viscous stresses. But viscous stresses can modify the waveforms because they are deformable, they're elastic. But if you now change the geometry of this beating pattern, you will feed back to the dynamics of the molecular motors, which in turn give rise to this beating pattern. So through this feedback loop, they can spontaneously adjust their phase and get phase lock. You can do the same thing for cilia. So here is we have cilia that's beating initially anti-phase, that's at time t is equal to 0. And if you just again wait long enough, I will show you the final waveform. So a long time, so t is equal to t infinity, you see this conformation is beating in phase. So that's again a spontaneous phase synchro. We can be a bit more quantitative about the whole process and define what's called the phase of the oscillator, that's psi. And if you know the phase of the oscillator, you can compute the phase difference, that's denoted by delta. And like I showed you in the movie, the delta goes from an initial antiphase conformation, that delta is equal to pi, to an in-phase conformation of delta is equal to 0 over time. It turns out that you can capture this time evolution with the simplest possible dynamical system you can imagine, that's called an Adler equation, is delta dot is equal to epsilon sine delta. And depending on sign of epsilon, you can either have in-phase or antiphase component. So it's natural to interpret this epsilon as a coupling constant of this problem. So you can fit this dynamical system to this data, that's what we do over here, and then estimate this coupling constant. And then plot the coupling constant as a function of the separation distance between these two pair of interacting filaments. So I increase the distance between the interacting filaments and plot the coupling constant. And as you can see, in far field, it decays as 1 over distance. Now that's really nice because interactions in Stokes law are computed through Green's function, and this Green's function themselves decay as 1 over distance in free space. So this kind of embodies this idea of hydrodynamic interaction and solidifies what's the role of interactions in phase synchronization. Okay, all the molecular processes that I was describing, this attachment and detachment of molecular motors, they have biochemical noise that's intrinsic to this process, and that's something that also we can incorporate in our model. In presence of noise, this precise idea of synchrony breaks down, and you have fluctuation around the phase lock conformation of delta is equal to that we see over here. And as you increase the separation distance between the two filaments, you increase the amount of fluctuations in the problem. It's captured over here. And this kind of behavior is well captured by a stochastic version of the Adler equation that I just presented. So essentially you have delta dot is equal to epsilon sine delta plus some multiplicative noise in the problem. You can define the associated Fokker-Planck equation with at the stochastic Adler equation. And that's shown over here, where P is the probability distribution function for the phase difference delta, and D is a diffuse. In steady state, you can actually compute the probability distribution function analytically, and that's the expression that I've shown over. Now let's do a numerical experiment. We now keep the distance between these two pair of filaments fixed. So small d is now fixed. I'm not changing the distance. But now I numerically crank up the amount of noise that you have in a problem. So that's lambda is a numerical parameter that governs the amount of fluctuations you have in a problem. And I'm increasing that. Now over here, I'm plotting the phase difference delta as a function of time. So what we see is that for weak noise, this is the ground curve over here, you see that they're fluctuating around this phase lock condition of delta is equal to 0 with very small fluctuations. But as you increase the noise, there is this events where suddenly there is discontinuities on this phase difference. And these discontinuities correspond to the fact that one filament kind of forgets about the other, gains a complete phase of plus or minus 2 pi, and then again gets phase locked. And these events are called phase slips. So if you keep the numerical noise parameter even further, you can see that there are frequency of phase slips are increasing and you have a lot of these discontinuities. So what we can do now is that you can study a long time statistics of these kind of processes and numerically compute what P of delta should be in steady state. And that's what we do over here. And then we define an effective potential, which is just negative log of P delta. That's shown over here. That's the effective potential. The symbols are from not experiments, right? Symbols are from simulations, and these lines are from my theory. That's the analytical experiment. So we get a very good fit. But what's actually nice about this interpretation is that it gives you a minimal description of what a phase slip actually is. So think of this potential as harmonic traps, and you have a Brownian particle sitting in one of these harmonic traps. So if the noise is weak, then this potential is very well defined. It has a sharp peak. And and a very large barrier. So the Brownian particle cannot escape and it remains at this phase lock condition of delta is equal to 0. It's more fluctuating. But as you increase your noise, you reduce the barriers of this harmonic trap, and then also the well gets flattened, and then the Brownian particle can escape from this well and hop into another well from delta to delta plus or minus 2. And these noise assisted hops in this system is what corresponds to phase slips in the actual full system. There are some other results on frequency of phase slips that we can also compute, and there is a very good agreement with theory and numerics, and let's keep that. And we'll try to sum up this section. Okay, so I told you about how spontaneous oscillations emerge in this kind of problems. Okay, I told you an active filament problem, and then I've discussed interaction between pair of filaments, and also told you about what's the role of biochemical noise in these fluctuations and in the process of synchronization. So what's next? It turns out that in this business, one filament is interesting, two filament is, but then you have to do kind of 100 filaments. That's something that we have been trying to do for a while. Here's a very preliminary result. It's an array of cilia that's interacting through hydrodynamic interactions. And you can see kind of that they are spontaneously generating these waves or metachronal waves that emerge collectively. Okay. So I think I have a bit of time to talk about the other problems that I worked on. And the first problem that I did was studying dynamics of actin filaments in simple shear. And this was again done in a collaboration with Brato, France. And it turns out that simple shear is not really simple. You can decompose it into a rigid body rotation plus a straining component. That's shown over here. If you place one of these filaments in this flows, then they periodically or quasi-periodically tumble in presence of fluctuations. And that's a very famous or classical result of Stokes' law called Jeffrey's orbits. As they tumble, however, they experience compressive viscous forces. And if the flow is sufficiently strong, then these viscous forces can induce Euler buckling instability, giving rise to this C-check confirmation. You can see over here. And if you keep on increasing the flow strength, then you find this hairpin confirmation that's emerging in this problem. Let me show you a movie. Here you see that there is a tang trading motion of these filaments. And even you can see higher order buckling modes like an S. What really got us interested about this problem is we can actually compute microscopic stress tensors for this instability and relate these stresses to bulk scale rheology problems. So we were interested essentially in rheology of dilute suspension. That's why we started studying these problems. But when we worked, we realized that a lot is not known about these morphological transitions or these instabilities themselves. So we spent a lot of time developing reduced order models that can analytically predict different dynamical behaviors of this filament and also predict onset of different morphological transitions and instabilities. So more recently, we have gone back to this question of the rheology of filaments, and it turns out that this kind of buckling instability results in shear thinning and normal stress differences. So if you're not familiar, here is a one-line definition. You take water, you shear it, and the viscosity of the water is not going to change with shear rate. That's an intermediate fluid. However, if the fluid has polymers, the viscosity can decrease with increasing shear rate, and that's called shear thinning. And the everyday example would be ketchup, and often these kind of properties are derived. To illustrate positive normal stress difference, the classic experiment is what's called the Weisenberg effect. You have a plane solution over here, there is a rod, and that's rotated. You see this movie. And as this rod rotates, it's not rotating. Okay. As this rod rotates, the polymer that is suspended in the strain gets stretched, and this induces hoop stresses that kind of pull this liquid off the rod. And that's called a rod climbing effect. This is very classical signature of positive normal stress difference. So what we can do is that we can compute the stress tensor in these problems, and that's what I'm doing over here. This black line over here is a case for a rigid rod, which is not deforming or not buckling in this flow. And as you can see from this picture, for a rigid rod, that over a one period of tumbling event, the average normal stress difference is zero, because it cancels out the symmetry. On the other hand, this colored line is for a buckling filament, and when it buckles, this results in this positive normal stress differences and also shear thinning. So this is a very preliminary result that I can show you. So looking at viscosity as a function of shear rate, you can clearly see that viscosity is decreasing. That's evidence of shear thinning. And what we're trying to do is that we're trying to understand how buckling instabilities alter classical rod-like suspension scaling laws or theories. So these lines are from classical rod theories, done by Diehl, Hinch, and Brenner in 1970s. So we're trying to understand how these things are altered in buckling. Okay, so there are a couple of other problems. These are not related to the story that I've been telling you so far. This is understanding transport of active and passive particles for solving the dispersion, and I particularly used what's known as generalized Taylor dispersion theory to do these problems. It's a theory developed by Howard Brenner. For passive particles, I looked at how these things asymptotically transport or diffuse in peristatic flows. And for the active particle problem, I studied this in two-dimensional lattices. And this was done in collaboration with Brato, who was a grassroots in the group, and a lot of you know him actually. I should mention that a lot of credit actually goes to Roberto for developing bulk of the theory which extends this generalized Taylor dispersion problems for active particles like material suspension of separate particles. More recently, I'm looking at this transport of polymers in two-dimensional porous media, and this is done in collaboration with Charles, who's a visiting master student from France in our group. This is just a fun problem to study because the dynamics is very rich, but there are some interesting applications as well. So in suspension, it's often important or interesting to separate out polymers that have different properties. So if you have a suspension with two polymers of different length or different stiffness, it may be interesting to how to separate them. So that's kind of microstructured arrays can be used to do that. Just to illustrate that, over here you see a flow in this direction of the arrow. There is a large polymer and there is a short polymer. These circles are just rigid obstacles. So if they are moving, see what happens. The large polymer gets trapped around this obstacle, remains wrapped, and its transport is hindered, while the short polymer can glide and slide and escape quicker. So this is like a chromatographic separation problem that we have with these devices. And we are trying to convince our collaborators to do some experiments with this. Okay, so I think I'll try to end with a perspective, and I thought I will use a quote of Huygens for that. So for those who don't know, Huygens was a very famous French theoretical physicist. He's known as the father of soft matter physics. And he won the Nobel Prize in 1991 and worked on this very famous polymer physics problem called the coil stress transition. It's not really important in this context. But here's what he had to say in his Nobel Prize lecture. So he says here, by here he means coil stress transition. Here we see another fascinating aspect of soft matter, the amazing coupling between mechanics and conformation. And I think that's the theme that kind of inspired all the problems that I described. So there is viscous stresses, there is velocity stresses, and sometimes there can be activity that dictates conformation or morphologies of the filament. But the morphology in turn dictates mechanics. If you think of rheology, then the morphology decides whether it should be shear thinning or normal stress differences. If you think of collective behavior or emergent properties of phase synchronization, then it's also the deformation of the structure of the filament that dictates mechanics. And this coupling of mechanics and conformation leads to really a plethora of interesting problems, some of which I've tried to study. I think it's a good way to sum things up. Okay, I should thank everyone who made this work possible. I'd like to start by thanking my advisor. That's not because it's a convention to say good things about your advisor that I've done, but I've been really fortunate to work with him over the last 4.5 years. He's given me a lot of independence to pursue what I want to pursue, what I like. Never to worry about resources, funding, which problem is fundable. It's been a very good learning experience, and he's been also very patient with results. So that's taken a lot of pressure off. I want to thank my collaborators at the SPCI. Yana did all the experiments with these actin filaments. Ank and Olivia PIs in France, and I'm really grateful to them for this collaboration. They've been extremely kind, inviting me to visit Paris 3 times now. So it's a very fruitful collaboration. I want to thank my collaborators at University of Tulane who did non-Brownian simulation with fibers in this helical walking problem that I showed you. I want to thank all my committee members for agreeing to serve on the committee, for tips, suggestions, and comments on this work. I want to thank all the group members for interaction and learning a lot of things over the years. A few of them are here whom I'm not expecting, so I'm glad you guys are here. I want to thank friends at SME who write up usual days. And there's a very good group of friends in San Diego whom I really relied on everything. They are also here today. It's very nice. I want to thank my friends from undergrad they're living my lifetime and supporting me a lot. And finally, I want to thank my parents, my uncle, and my girlfriend Shreya for making everything possible. I wouldn't have been here without them. See, these are some of the manuscripts that has resulted from the work, like they mentioned. Some has been published, one is under preparation, and a couple of them to be submitted. And with that, I will finish. I think I finished a bit fast. Good questions.
First, we'll take questions from the audience, if there are any. No questions from the audience. Okay, so let's thank Brato again, and then I'll ask you at the end.